Okay. Um, okay. So we are in week 11, and we're going to look at the notion of integrals. This is integrals over curves and surfaces, and arbitrary volumes. Okay. So before we start, let me just define the notion of an integral um, over uh, over the real line. Okay. So so what is integral technically? If you have a function and you are taking the integral over over an interval uh, of the real line, then that essentially is um, it is basically what we call a Riemann sum. So Riemann sum is that if you're integrating a function f over an interval I, then you consider an arbitrary partition of of this interval. So let's say I is an interval a comma b, and you consider all possible um, and you consider all possible uh, partitions. Okay. Okay. So you can consider, let's say P is a partition of I. So you can consider partitions of I, simple partitions of I, which are of the form some uh, A0, A1, up to let's say some AN, where A0 is A and AN is B. And then this integral is effectively it is a it is a Riemann sum, which means that it is actually supremum over all such partitions that you get, and then it's a sum where you take, let's say, you take the infimum of f over a particular uh, over a particular uh, interval. So this is, let's say, ai minus 1 comma ai, where I is equal to 1. Okay. And this is over all possible uh, partitions. So of course, if this quantity exists, and uh, and you can consider another equivalent quantity, which is this quantity, which is the infimum over all partitions P. I is equal to 1 to n, the supremum of f over ai minus 1 ai. Okay, so We say that the function is Riemann integrable if of course it can be represented as the Riemann sums, and these two quantities actually turn out to be the same. Now, when you uh, when you have curves and surfaces over arbitrary the curves and which is like arbitrary sets over Rn. Now, the notion of integral, uh, it is uh, it is still a kind of Riemann integral, but there is a notion of a density function that we also add in. So let me tell you what that means. So let's say you have a curve. Okay. So what is a curve? A curve is essentially a mapping. So a curve, you can think of it, is a mapping of some interval into some Rn, right? So C is my curve. Okay. So essentially what is happening is that you have this interval over here, which is getting mapped to some curve, which is sitting in Rn. Okay. So now what is happening is that when you are, uh, when you are, let's say now you have some function f, which is defined on this curve. Okay. So you have this interval a comma b, which is getting mapped to this curve, which I'm calling C. Um, or let me call this curve alpha instead of C. That's clear. And then you have a map which is defined from alpha to R. Okay. Now, so if you compose this, you get a map from A comma B to R, right? So you compose these two mappings. So you basically have F composed with alpha, and that gives you a map from A cross A comma B to R. Okay. Now, normally, you could say that um, you could define the integral of a function f over over this uh, over a comma b as just this integral over a comma b f dot alpha dt. Okay, because I have a map from a comma b to r. Okay. Now, but the thing is that this is actually not well defined. This is why is this not well defined? Because it depends upon the choice of parameterization of alpha. So think of alpha as a subset of Rn. Okay. So if alpha is a subset of Rn, uh, it is a curve. You could have multiple such parameterizations of the same curve. Okay. So for instance, instead of having the curve defined from a comma b to alpha, I could also have the curve defined from 0 comma 1 to uh, to Rn. Okay. Okay. So in other words, what is possible is that the the curve should be thought of as the image of a map. Okay. Uh, but uh, but the domain of this curve alpha could be a comma b, it could be any other interval in Rn. And on top of that, you could use various other parameterizations. So for instance, we saw last time, we saw what we call the arc length parameterization of a curve. So the arc length parameterization of the curve is a parameterization where the velocity along the curve is one. Okay. So recall that the arc length parameterization is um, so it's a parameterization where the um, the norm of this tangent vector, which is the velocity, or not the velocity, but the speed rather, So that is actually equal to 1. You can call that alpha dot. That is equal to 1. Okay. Now, so of course, the question is, if I think of the curve as a set that is in Rn, then the value of the integral should be independent of the choice of the parameterization, right? And therefore, this is not a correct notion of integral, because this is dependent on how you parameterize that set S. So you should think of the set S over here as just a curve which is sitting in Rn, but your integral should be independent of how you parameterize the curve. So in other words, let's say you have a curve over here, okay, and you could traverse this curve with a velocity of 1. Okay. Now let's say if you traverse the curve with a velocity of 1, it takes, let's say, t units of time or L units of time to cover the whole length of the curve. Okay. So maybe like this is a parameterization of the curve. So let's say gamma 0 comma L to Rn is one parameterization of the curve. But if you drop your speed to half, then it is possible that then you likely going to take twice the amount of time to cover the length of the curve. So you could have another parameterization of the curve where you take 2L time to reach Rn. Okay. So now what happens is that because the set is the same, but you have two different parameterizations, the integral should also be independent of how you parameterize the curve. So the appropriate way to define the integral is actually, so let's say gamma is a curve from A comma B to Rn. Then we define the integral of f over gamma as equal to integral over A comma B f of gamma t times the norm of the tangent vector. Okay. Now, why is this independent of the choice of parameterization? So let's say you used a different parameterization. Okay. Uh, let's say you used a parameterization where I write my t as a function of some other variable s. Okay. So then what would this be? You're doing a change of variable of this integral. So this is integral a comma b f of gamma of t of s times gamma dot. Gamma dot is basically d upon dt of gamma norm. But you have dt, which you will write as equal to t dash s ds. Okay. But if you notice what this quantity is, this particular quantity uh, is just equal to d upon ds of gamma of t of s. So what is this quantity? If you evaluate this, this is equal to d upon dt of gamma times t dash s. Okay. So you were supposed to put a norm of t dash s over here. And so indeed you get that this quantity is basically this. So you can just write it as equal to integral of a comma b f of gamma of t of s times d upon ds of gamma of s. So when I say gamma of s, you just mean that this is equal to gamma of t of s ds. Okay. So of course, if you define this in this way, then it is independent of how you how you parameterize the curve. Okay. So let us solve one problem which is related to this. This is the notion of a um, of um, of work done against a force. So let me just write now. This is already something you would have seen in physics, which is work done by a force. Okay, so this is a bit different, but we'll see this is how this is defined. So your force is not a scalar function. Force is a vector field. Okay. So to give an example, let's say you have a curve like this, and you have some kind of a force. So force is a vector field. So let's say it's defined like this along the curve, and the work done is basically defined as, so this is your force F. Let's say this is your curve C. Then it is defined as integral over C F dot dr. Okay. So this dr, so let's say you choose a parameterization of your of your curve. So let's say C from A to B, or let's just write okay, let's use C from uh, okay, let's just for sake of simplicity write from 0, to Rn is the curve. This is a parameterization of the curve. Then then what this is equal to is basically F, which is this vector, the inner product of this vector with the tangent vector. Okay, which is so the tangent vector is basically C dot is equal to C1 dot up to Cn dot. Okay, so this is F comma C dot. Then you take the inner product dt. Okay, and this integral is over 0, 1. 0, 1 is how you parameterize the curve. Okay. Now, of course, the question is this independent of the choice of the parameterization of the curve? So had I parameterized the curve in a different way, would I get a different answer? So let's see. So again, let's say I use a different parameterization. So let's say I write t is equal to some t of s over here. So what we have is basically integral of f comma c dash t dt. If I use a different parameterization, I have integral of f comma c dash t mod of t dash s. Um, ds. Okay. Uh, so this is what I get if I if I just do a change of variables. Okay. So this is change of variables. So the change of variable is basically I'm using the substitution t is equal to t of s. Okay. Um, Now, what if I had a now of course the other now I have reparameterized the curve. This is not a reparameter. This is just a change of variable. Okay. Now, had I reparameterized the curve, I would have got integral of f comma d upon ds of c of t of s ds. So that is equal to integral of f comma c dash. When I write c dash t, I mean d upon dt of c of t times t dash s ds. And so you can just pop this out. So you get integral of f comma d upon dt of c of t of s times t dash s ds. Okay. So you see that there is a difference. The difference is that here you have a mod of t dash s, whereas you simply here have t dash s. So for the quantities to be the same, what we need is that t dash s should be positive. So now, can you say what this means? So we require t dash s to be positive. Then only this t dash s would be equal to mod of t dash s and we'll be fine. So what this means is that, let's say you you have a curve. Let's say this is your curve C. Now the curve is a set. Okay. Now you can traverse the curve in multiple ways. Let's say this is one way to traverse the curve. You could also traverse the curve in the opposite way. Okay. This is also another parameterization of the curve. Okay, so let's say this is your let's say this is a closed curve for the sake of it. Okay, and uh, you could travel in the same direction or you could travel in the opposite direction as well. Okay, so and what we know for a force is that if you if you uh, if you if you go in the opposite direction, then the work done would turn out to be equal to negative. Okay. And this is precisely what the relation tells you is that if you do a reparameterization, you require that uh, you are traveling in the same direction as you were before. So this is given by this is essentially meant by this relation that t dash s is greater than zero. Essentially, it means that as s increases, t also increases. So you are moving in the same direction as in the two cases, basically. Okay, so I hope it's clear. I'll give you one problem. Problems are actually quite routine, so there is not anything that you should worry about. Um, so here you have a problem, which is you have a force field over here, and you define the curve. Okay, so what is your curve over here? I'll just write down the curve and fit it into this formality. You can complete the integration. So C is a map from 0, 1 to R3. Okay. And C of T is basically given by T cube 2T plus 1 and T squared. Now you have a force field, which is F, which is given to you. So the work done is integral 0 to 1 f dot product with c dash t dt. So your c dash t is equal to 3t squared, 2 and 4t. Okay. And when you're writing f, so f is basically f is equal to f of x, y, z. It's a function of x, y, and z. But because you are on the curve, so it's a vector field along the curve. So this, you will use the coordinates of the curve. So just going to write it. So it's integral 0 to 1 f of, use the coordinates of the curve, which is pq 2t plus 1 and t squared, dot product with c dash t. Okay, so this is dot product. I'm going to use angular brackets for that. Okay, you can complete the integral. Okay, so I hope you have, so I hope it's clear. Then we can try to look at some other problems. Right. So oftentimes when we talk about these curves and so on, what we mean is that it is a diffeomorphic image of uh, of of an interval 0 comma 1. Okay. Um, if I give you like a weird looking curve, okay, uh, I mean some of these curves are actually good curves, but let's say you had like a weird looking curve which intersects itself in multiple places. So let's say you had a curve which looks like this. Sorry. Let's say you had a curve which looks like this. Okay. This is also a curve, and but it's this curve is not a diffeomorphic image of a comma b, right? Um, um, yeah, but that's not really a problem. You could still use uh, uh, the techniques that we have over here and define a parameterization and do the integral. Okay. What is a nice example? I don't really have an example at this point. Uh, hmm. Okay. The techniques here would remain the same. Actually. Okay. Now let's move on. Okay. Let's look at this problem. So again, you have a curve which is, yeah, yeah. If you have a question, yes. What is your question? You can unmute your mic and ask the question directly instead of typing it. Okay. No, I mean it need not always be a diffeomorphic image. So for instance, if you see a curve like this is not a diffeomorphic image. Okay. But as long as it is a piecewise diffeomorphic image, you can still do the integral. Okay. Is that's what I mean to say. These are not a curve like this is obviously not a diffeomorphic image of I, right? This is not is obviously not diffeomorphic to uh, is obviously not diffeomorphic to I. Okay, and it's a good question that you have asked. For instance, let's say you are doing an integration over a circle. Simple example is circle only, right? So let's say you have a function f and you are doing and you have the circle S1, which is um, which is given by r equals to 1, and you are doing integration of this function f on this circle S1. Okay. Now, of course, what is the right? Now, of course, what is the standard way to do this integral? You can use a um, just give me 1 second. I have to attend a call. Just give me 1 second. Yeah, sorry. So okay, so your curve is over here is equal to x equals to cos theta, y equals to sine theta. So of course the norm of the tangent vector is equal to 1, and you kind of write this when you are writing this, you will often write this as equal to integration of theta, where theta runs from 0 to 2 pi of this function f as a function of theta, d theta, right? This is how you're going to write the integral. But if you observe carefully what you're doing over here, see 0 to 2 pi, if you consider the range 0 to 2 pi, okay, this is obviously not uh, diffeomorphic to the circle, right? This is obviously not diffeomorphic to the circle. So the reason why this thing actually works is because you are essentially what you're doing is that if you take the circle and if you take out any one particular point of the circle, then this is diffeomorphic to the interval, right? So the circle uh, uh, is the interval with the endpoints identified. Okay, so, yeah, so right. I mean, uh, uh, it is basically the endpoints identified. But if you drop one particular point of the circle, since the point is a set of measure zero, and you are so if you're integrating this function f over S1, you can of course eliminate a set of measures zero. You can of course do integration of f where you do S1 minus some particular point that you decided to eliminate from this thing. Let's say you try to eliminate this point itself only, which is uh, 1 comma 0. So if you did this is of course going to be the same, right? Because it's a set of measures 0. But now, if you look at this particular set, this is a diffeomorphic image of uh, of 0, 2 pi, right? And you can do the integral there and you'll be fine. Okay. So this is basically the idea. So I hope it's clear. Yeah, I mean, subtly, yeah, I mean, there is a subtle point. The subtle point is that if it is a closed curve, right, then it is not, then it's definitely not an image of 0, 2 pi, or it's definitely not an image of a, I mean, then it's definitely not, uh, uh, yeah, I mean, it's definitely not a, um, right. I mean, it is definitely not a, uh, it's not diffeomorphic to the interval, right? So, I mean, effectively what you're doing? You're doing an integration over a measurable set, right? So, if you have a curve, you are basically doing um, an integral over that curve C, but the curve C, when you're doing the the integral over it, the measure that you are using is not the standard Lebesgue measure of R. Okay, it takes into account how the curve is embedded inside R Rn or Rk, whatever. Okay. Um, it depends on the embedding, right? And because it depends on the embedding, that is why you have that additional factor, which is the modulus of the tangent vector. Okay. So the modulus of the tangent vector that you see over there is basically a density that you are multiplying along with the Lebesgue measure on R. Okay. Um, so I mean, with this sounds a bit abstract, but it's actually very natural. So let's say you have an interval, okay, and this interval gets mapped into some curve like this. Okay. Let's say this interval also got mapped into some other curve like this. Okay. Now, of course, if you did not multiply this, let's say you have a function alpha 1 and you have alpha 2. Okay. Now, of course, the thing is that if you did not take into account this alpha 1 dot, which we also multiply with the function. So when you're integrating that, this is equal to f of alpha 1, then alpha 1 dot dt. If you did not take into account this, then you would not consider how the curve is embedded in Rn. Okay. Uh, you would just be pulling back this function f from this space which is Rn to the interval. Okay. But that's not that's actually that does not capture uh, intrinsically how the set is, right? So for instance, if your function uh, was just the unit function, is just the unit function. So then this would give you the length of the curve. Okay. So let's say if f was just identically equal to 1, then you get the length of the curve here, you get the length of the curve here. Okay. But if you did not multiply this alpha 1 dot t, and if you just pulled it back, then you get the length to be same for both these curves. Like, so both these curves, so let's say this is 0, 1. So then both these curves would come out to be equal to length 1, which is not correct, right? They are that would completely ignore the geometry of how the curve is embedded in space. So that's why we use this alpha 1 dot t term over there. We're going to see more of this as we move on to surface integrals, that what is that quantity that we need to multiply. Um, So yeah, so you need to understand that, well, if you know a little bit of measure theory, then you integrate a function over a space, and the space should have a notion of a measure that is defined on it. Um, so of course, when we say a curve, we need to be careful what we mean by a curve. So you can think of the curve as a continuous image of 0, comma 1. Uh, that is a perfectly well defined notion. Um, we are also going to assume that um, it is a it is at least a C1 curve, so that you can define tangents, and the tangent vector is defined continuously along the curve. Okay. Okay. So here you have a curve. The curve is given as a graph of a function. Okay. So whenever you say you see perceives the curve in the xy plane, y is equal to 3x squared. So this is the graph of a function. So the function here, which is y, is equal to 3x squared, and the graph of the function is basically x comma y of x. So this is your curve. So so C is defined from 0, comma 1, which sends x to x comma y of x. So now you can compute the derivative, which is c dash x. So c dash x is equal to 1 comma y dash x, right? And so the norm of this c dash x, okay, you don't need to compute the norm. You have vector field over here. So your f dot c dash x is equal to uh, x squared y plus y squared times y dash x. Okay. And now you can simply integrate this over 0, comma 1. So the integral of f over this curve C is equal to integral over 0, comma 1 x squared y of x plus y squared y dash of x dx. Okay. And you can complete the integral, it's routine. Okay, so I hope this is clear. Yeah, I mean, this is a good example, this example. And so, again, the problems here are fairly basic, but they kind of show you how to solve certain parts. So let's say, um, so this is an example where the curve, so until now we have assumed that the curve is a uh, is a is a C1 image of 0, comma 1, but it will not be a C1 image. I mean, as long as it is a piecewise uh, it is a piecewise C1 function, it works. So this is an example of a function of an integral f over a curve C, where C is a piecewise C1 function. And what is this piecewise C1 function? So this is basically the boundary of this rectangle. So this is 0, this is 2, this is 0, comma 2, 0, comma 0, and this is 0, comma 3. Sorry, this is 2, comma 0. This is 0, comma 3. Okay. Right. So of course, this is a right. So of course, this is a continuous function. Um, when I say continu, I mean the curve is a continuous function, but it's not a smooth function. It's not a differentiable function because you have these four corners. Okay, where the where a tangent is not well defined. So instead, but yeah, I mean the computation here is fairly simple. So what you need to do is just you need to decompose it into like uh, four C1 components. Okay, so the four C1 components is this, then this, and then this. So it's just the integration of f over first this. If I call this as L1, L2, L3, and L4, and this is integral over L1 plus integral over L2 plus integral over L3 and then integral over L4. Okay, where um, so you can complete this integral. Okay. Okay. So I hope it's clear how to do this, right? So let's say I'll show you how to compute, let's say this one component. So this one component is what is this? This is L2 is basically the set which is x is equal to 2. And what is the tangent vector? The tangent vector over here um is just j cap only, right? So the tangent vector along L2 is just equal to j cap. So you just have to do integral of f dot j cap, and this so of course x is equal to 2 over here, and you have an integral over y where y varies from 0 to 3. So we just write it down, then that is equal to uh, minus 2xy dy integral 0 to 3. But x is equal to 2, so that is equal to minus 4 0 to 3 y dy. So this is going to be L2. Okay, so similarly you can do L1. L1 would be equal to L1, the tangent vector is along the x, so it's just I cap. So and y is equal to 0. So it's integral in x squared the integral x squared dx, and the range is from 0 to the limits are from 0 to 2. So this is integral over L1. And similarly over L3 you can do. And L4 is going to be 0 because L4 is along the y-axis, but x is 0 over here. So L4 would be 0. Okay, so you can do this integral. I hope you got how to do this. Okay. Now let's move on to surfaces. So before going to surfaces, I'll just state one result, which is called the divergence theorem. It's a very important theorem, and this is a theorem that appears time and time again in analysis. It is one of the foundational cornerstone theorems that are there in analysis altogether. So this is the divergence theorem. So the divergence theorem basically states that if you have any domain omega, where omega is a subset of Rn, okay. So I mean, of course, the question is what are appropriate choices of domains of Rn and so on, and it's a bit technical, so I'm not going to go there. So you can think of omega as being a domain which is it's a nice looking domain. Okay, it's a loose term, but let's not worry too much about it. And let's say you have a vector field V. V is a vector field on R3. It did not just be a vector field on whole of R3. It could be defined on omega also. It's enough that the vector field is defined just on omega. So then the divergence theorem basically states that the divergence of V over omega is equal to the integral over the boundary of omega, del omega, times V dot n cap. Okay, where n cap is the, I'll tell you what this is. This is the outward pointing norm. So so if you're doing, let's say you have like a bounded region over here. Let's say let's say this is a bounded surface. Okay. And the normal over here, let's say the normal is the outward facing norm. Okay, so let's say you have this boundary del omega. So this is your interior omega, and this is the boundary of it. We call it del omega. So del omega is basically, assume for now that let's say del omega is a closed surface which bounds a particular volume, which is omega, let's say. This is not a criterion for the theorem. The theorem holds for more arbitrary domains also. But now, for now, assume that you have a closed surface, which is the boundary of this volume omega. So then n cap must be the outward facing norm. Okay. Of course, I mean, for some things like these to be well defined, you need that the surface S has to be a two-sided surface, which means that it has to be an orientable surface and all those things. So we're going to assume that this is an orientable surface. It's not like the boundaries, the notion of boundary is not well defined and things like that. So yeah, there are of course some technicalities over here, but um, you don't have to worry. I mean, over here, I mean, for the purpose of this course, it is sufficient that you will get like nice looking domains only to work with. So I hope you got the statement of the theorem. Uh, Now, the question is, how does this theorem help us? So let's say now we come to this point, which is integrating. Integrating a function over over a surface, let's say. So let's say you have the unit sphere. Let's say you have the unit sphere, and you want to define the integral of some function f defined over this unit sphere S2. Okay. So of course, this is the way this is defined is actually as follows. So okay, just give me 1 second. Okay. Well, I have to use a term over here, but I'll tell you what that actually means. We're talking a little bit about more general surfaces. Maybe for the purpose of the course, you'll get like simple problems in your exam, but it's good to know what it means generally. So we define if we have a function f defined on a manifold M, which has a metric G, then this metric basically turns this manifold into a measure space. Okay, and and you have the uh, and you have a density uh, which is induced as a result of this metric. Okay. So the integral over f for this manifold M, okay, is well again uh, you need to know how you define an integral of a function over a manifold in general. So the way in which we do this is through charts, right? So I'll give an example what this is. Maybe this is probably not too relevant. It's a bit general, of course. So let's say you take the example of a sphere. Okay, this is your sphere S2. S2 is the unit sphere in R3. Okay. Now your sphere is not, of course, not equal to R2. It is a two-dimensional surface, but it is not, of course, diffeomorphic to R2. So what you do is, or one thing that you can do is, let's say you have to integrate a function f over the sphere. So you can sort of divide the sphere into two parts. Okay, you have the the upper hemisphere of the sphere, and you have the lower hemisphere of the sphere. Okay. Um, so the sphere is given by the equation x squared plus y squared plus z squared is equal to 1. Okay. Um, if you divide the sphere into the upper hemisphere and the lower hemisphere, so then you get two parts where one part is given by xy, uh, 1 minus x squared minus y squared. So this is the upper hemisphere of the sphere. Let's call this S plus, and let's call this S minus. So S plus is basically this, and S minus is basically xy minus of 1 minus x squared minus y squared. Okay. So what you have done is that you have the sphere and you have written the sphere as a union of S plus and S minus. Okay. And but the thing with S plus and S minus is that S plus, let me just write it down, S plus and S minus are graphs of a function from R2 to R3. Okay. So you can see that this is a graph of a map. This is also a graph of map. The map is xy, 1 minus x squared minus y squared. And for the other case, it's minus of that. So S plus and S minus are graphs of maps from R2 to R3. Okay. Now, of course, if you want to integrate this function f over S, I'm just going to write S instead of S2. You just understand this is S2 only. But it doesn't have to work for S2, it works for Sn also in general. You could take the n-dimensional sphere also, it works there. So you can write this function f as f over S plus and then f over S minus. Okay. So you're integrating it over the upper part, the upper hemisphere, and then you're integrating it over the lower hemisphere as well. Okay. Now, when you are integrating this function, let's say you take this part, which is integral of f over S plus. Okay. So this is actually a map. You can actually plot this. It's a map uh, which is basically the upper hemisphere of the sphere. Okay. So it takes a point x comma y and sends it to x y 1 minus root over 1 minus x squared minus y squared. Okay. Yeah. Probably. Do you have any question? Okay. So now, so as before, what? Yeah. So as before, what we did for a curve was that we had a function on a curve, but you could write the curve as, or you could write a portion or a piece of the curve as a as an image over right. I mean, you could write a portion or a piece of the curve as a uh, uh, as an image over I. Here also, you can write a portion or a piece of the surface as an image or a graph of this particular function, which in this case is xy at root over minus x squared minus y squared. So now you could pull this function back. Uh, so this function, which is defined on S plus, could be pulled back to a a domain of R2. Okay, let me write it down. You could pull it back, pull it back to a set in R2. So what is that? So what is that set? So the set is basically the unit disk in R2. Um, right. I mean, essentially this S plus is a uh, graph of a map from D from D2, right? And so this map is basically x comma y. So the graph of the map is x comma y. So basically the map is x y goes to 1 minus x squared minus y squared, and S plus is just the graph of this map. So you could pull this map back to D2. Okay. So essentially S plus is diffeomorphic to D2, right? And you have this function f, which is defined from S plus to R, and you can pull it back to D2. So you do an integration. So this integral of f over S plus is basically integral of f over D2. Okay. So let's say if you have f x y z, then you have essentially pulled it back, right? By writing z as a function of x comma y. Okay. And now you know how to do this integral because of course, um, uh, we have solved these kinds of integrals in our previous classes. However, the thing is that uh, you simply cannot do such a thing because just as for the curve, this simply does not take into account how D2 is embedded in R3. Okay, so this is an embedding of D2 in R3, which is the upper hemisphere of the disk. You could also have a very different kind of an embedding. Okay, you could also have an embedding which looks like something like this. Okay, this is also an embedding of D2 in R3, which has a completely different geometry. So you also have to take into account the geometry of this embedding. Okay, So for the curve case, we took into account the geometry of the embedding via the use of the tangent vector, right? So you had a uh, so you had the tangent vector in this interval 0, 1. So what is the tangent vector? There's only one tangent vector, which is the tangent vector along the direction of along the direction in which t increases. You took it and you mapped it to gamma dash of t, okay, and then you took the norm of it, okay. So essentially, this what this captures is how much stretching that there happens, okay. So um, if you had a stretching of dt over here, this captures, this is only loosely what I'm saying. The more formal language is a bit technical and we need to introduce a lot more stuff. So I'm ignoring it now. So essentially, this captures how much stretching has happened. Okay. So here also you need to take into account how much stretching has happened. Okay. And the way to basically do this is as follows. Um of course, you no longer have just an interval. Uh, you now have a subset of R2. So what you do is that so you have two. So essentially, you have two directions now. There's a direction in which x increases, and there is a direction in which y increases, right? So whatever your map is, so in this case, let's say you have a map. So let's call this map as phi1. You construct the Jacobian of that map. So you construct d phi1. Okay. So d phi1 is going to be this 3 cross 2 matrix. Okay. So you're going to have two columns. Okay. So what does this first column represent? So okay, let me just write it down. What this d phi1 would look like. So this d phi1 would basically be it has three components. So this is basically del x of, okay, let's not call this phi1. Let's just call it phi only. So this is del x of phi1, del x of phi2, del x of phi3. Here you have del y of phi1, del y of phi2, and del y of phi3. Okay. So what do these two columns actually indicate? So the two columns indicate that if you have this vector, think of this is R2, okay? So this is R2 and you have two vectors, okay? There's one vector which increases the x direction, and then there's one vector which increases the y direction. So think of the unit vector in the x direction. Let's call it x cap, and take the unit vector in the y direction, y cap. So what this basically means is that x cap has been mapped to del x phi1, del x phi2, and del x phi3. Under this mapping. And similarly, y cap. So this map, essentially what this means is that d phi of x cap is equal to this, and um, d phi of y cap is equal to del y phi1, del y phi2, and del y phi3. Okay. So here if you have x cap and if you have y cap over here, then they together were forming a unit square, okay, whose area was 1. Okay. Now you have two vectors. So let's say this is your sphere, this is your surface, and let's say you had one unit vector here, one unit vector here, and this unit vector got mapped to some unit vector here and some unit vector here. Okay. So now if you considered a very small unit vector, which so let's say I have a very small unit vector, let's call it del. So I have del x cap and I have, let's say, del y cap. So then this del x cap and del y cap were together forming a small area element over here whose area was a del square, right? Here, here also we have to essentially take into account what is the corresponding area element that they are going to. So this is going to be the differential area element. Okay, and the way you essentially compute it is that um, you take what is called an outer product of it. But I'll just give you the formula instead of instead of deriving everything. Um, right. Just give me 1 second. Just give me 1 second. Um, just give me 1 second. I'll be back in 1 minute. Yeah, sorry. So, right. So the way you compute the volume element now, so so you have to build the analogy for uh, you have to build the analogy with curves. So for curves, what happened was that we took dt and we scaled it by this factor gamma dot t. Okay. But now you don't just have like a length, you have like two directions, let's say del x cap and del y cap. And so the factor that you have to multiply with is basically as follows. Uh, you consider you consider this matrix d phi, okay, and you consider all 2 cross 2 determinants of this matrix. So sorry, 2 cross 2 submatrices of this matrix. So what is a 2 cross 2 submatrix? So let's say you consider this part, you consider this part, and then you consider this part. Okay. So I'll just write what this is. So this is um, you consider three 2 cross 2 matrices where one matrix is 1 comma 2, one matrix is 1 comma 3, and the other matrix is 2 comma 3. So 1 comma 2 means you take the first and the second rows of d phi. 1 comma 3 is the first and third rows of d phi, and 2 3 is 2 comma 3 of d phi. Okay. So what this is basically doing is that I mean this will just introduce more linear algebra, but you are taking this d phi of x cap and you're taking this d phi of y cap, you're taking these vectors and you are doing and you're taking a wedge product of the two. Okay. So the wedge product of the two is basically, and then you're taking a norm of this. So the norm of this wedge product is essentially the area of a parallelepiped. Okay. So you had a small rectangle over here, which got mapped to a small area element over here. And the so if this was, let's say, this was like a tiny del x cap, and let's say this was a tiny del y cap, then this thing got mapped to del of d phi, and this thing got mapped to yeah, I mean this is yeah, d phi of x cap, and this thing got mapped to del of d phi of y cap. And then this area element over here is basically given by this. Okay, to compute this thing, because I'm not going to tell you what this is. To compute this thing, what you do is that you consider all 2 cross 3, you consider all 2 cross 2 submatrices of them. Let's say d phi 1 2, d phi 1 3, and d phi 2 3 are those 2 cross 2 submatrices. And then you take the square of their determinants. So determinant of d phi 1 comma 2 squared plus d phi 1 comma 3 squared plus d phi 2 comma 3 squared, and then you take the square root of that. Okay. So this is so this is basically the factor that you have to multiply it with. Okay. If you want to like quickly draw an analogy with curves, so let's say gamma was a curve. So then your Jacobian matrix simply look like gamma 1 dot, gamma 2 dot, and gamma 3 dot. Okay. So sorry. So your Jacobian matrix over here would have looked like um, it would be a it would be a 3x1 matrix, which would be looking like gamma 1 dot, gamma 2 dot, and gamma 3 dot. So you have to form all 1x1 submatrices of this. So your 1x1 submatrices would just be gamma 1 dot, gamma 2 dot, and gamma 3 dot. Okay. And then you have to take the square of their determinant. So that would be equal to gamma 1 squared plus gamma 2 squared plus gamma 3 squared. And you take half of that. So that is just equal to the norm of the tangent vector. Okay. Here, this thing gets generalized into a formula that looks like this. Okay. So, right. So the rule to do the integration is as follows. You decompose this function, you decompose the whole surface that you're working with into components which can be written down as graphs of maps. Okay. So in this case, the sphere can be written into two parts, S plus and S minus. And when you're doing the integration over S plus, you can then pull it back to R2, but you also have to multiply with a factor like this. Okay. So this factor is basically the Riemannian volume element, which I'm going to call it dVg. Okay. So the integral over here is basically to summarize what is going to be F over S is equal to F over S plus F over S minus. But F over S plus you can write down as F over D2 times this map. So whatever this map that you got for S plus, you let's give it some kind of a name to this. Yeah, I mean, let's just for now, let's just call it as d phi norm. Okay, just for the sake of it, this is not a standard definition by any means. So you would just multiply it with d phi norm. Okay, plus integral over f. The S minus you also change to D2, but you have a different map over here. And for that different map, you put D phi norm again. Okay. And this is how you can complete the integral. This would be a different map. Okay. Because this map phi dash is this map x, y goes to minus of 1 minus x squared minus y squared. Okay. But you would say that there is no difference. You would see that once you compute this d phi prime, because the sphere is symmetric and whatnot, this d phi prime is actually going to be equal to d phi. Okay. So this is how you can then complete. You have this integral over the sphere, which you have then written down as a sum of integral over two parts, where each part is basically over D2, which is a subset of R2, which you can then do the integral because it's a double integral and so on. You can do this. So, okay, so this is one way to solve an integral like this. So this is the definition of integration of a function f over a surface S. Okay. Now, how does this Stokes theorem help us? I mean, this is a pretty involved process, right? It's going to take a long time to. You first of all have to think what is an appropriate way to split the surface into these parts, and then write down each part as an embedding of a subset of R2 into R3 and what all and what not. So it's a pretty involved process. So the divergence theorem helps us in the way that if you get an integral, which is integral of f over S, where this integral, where suppose you can write this integral as a dot product of some vector field x times the unit normal field on S. Suppose you can write it down in this way. So then the divergence theorem tells you that you can replace this thing with the divergence of x over the volume which is encompassed by this S. So if your S is the sphere S2, then this would be D3. And of course, you can then complete the integral because this is this is this is just an integral over a subset of R3, and um, you can just do the integral. It's just a multiple. It's just a triple integral. Okay. Uh, so basically, just to tell you how to finish this integral, you'd write this integral as x varies from um, -1 to 1, y varies from minus of 1 minus x squared minus 2 plus of 1 minus x squared, and then z varies from 1 minus x squared minus y squared to 1 minus x squared minus y squared minus, okay? And you'd have this function, which is the divergence of x times dz, dy, dx, okay? So this is how it would just turn out to be equal to, and you know how to finish this integral off, okay? So this is where this Stokes theorem helps us. It becomes a computational tool, okay? All right, so I hope you got some of this. I can pause for a moment. If you have any questions, you can ask me. Then you're going to look at a problem. Okay. Right. So you have an ellipsoid over here. Okay. Um, and you have this function which is simply it's given to you what this is. So it's just asking you to apply the divergence theorem, right? So let's apply the divergence theorem. So you have a vector field V, which is given by xy I cap plus yz j cap plus zx k cap. Okay. And you have you can compute the divergence of V. Divergence of V is given by del x of V. Sorry, it's del x of sorry. Sorry, it's actually del 1 of V1 plus del 2 of V2 plus del 3 of V3. So del 1 of V1 is Y, del 2 of V2 is Z, and del 3 of V3 is X. So the divergence is just X plus Y plus Z. So this is a direct application of Stokes theorem, which is the divergence theorem, which is integrating the function x, y, z over the volume, which is enclosed by the ellipsoid. Okay, so the ellipsoid is basically like a 3D version of the ellipse, and you have to integrate this function x over over the region bounded by this ellipse, over this ellipse side. Okay. Now, I just want to mention one thing, which is this is a purely computational thing, which is the way in which you define this parameterization actually influences uh, basically it influences um, it decides how easy or difficult it is going to be for you to solve this integral. Okay, so there is um, so one way to parameterize the sphere is is as follows. Okay, is basically by using polar coordinates. So you write z is equal to, so you pick these coordinates theta comma phi. You write z equals to cos theta. X is equal to sine theta cos phi, and y is equal to sine theta sine phi. Okay. Now, if you want to do the same procedure that we did, which is uh, which is um, essentially what we did for the last time. So if you write the Jacobian matrix, so the Jacobian, so what it does is that it takes this theta comma phi and maps it to Rn. Okay. Now this is not a complete description of the sphere. Okay, so if you just if you have the sphere like this, right? I mean, this in itself is not a complete description of the sphere, because what are your limits of theta? So your limits of theta are from 0 to pi, and your limits of phi are from 0 to 2 pi. Okay. Right. So essentially what you're doing is that you are eliminating a set of measure 0 from this sphere S2. Okay. And by doing that, you then have um, you then have a mapping of uh, of the sphere into this rectangle, which is 0 comma pi and 0 comma 2 pi. Okay. So if we just draw like a picture of this theta phi system, um, theta is from 0 to pi and phi is from 0 to 2 pi, let's say. So you have this rectangle. So essentially you have this rectangle minus the endpoints of this rectangle. Okay. Um, yeah. Just give me one moment. Okay. So you have this embedding of this into the sphere S2. And the part of it which is not covered by S2 is a set of measures 0. I think I think you need to take out a meridian of S2 so as to get S2 from this. Okay. Um, so now you can do this procedure for S2. In particular, you can compute the Jacobian matrix. So if you call this mapping as let's call this mapping as H, then you can write down the Jacobian matrix of DH, which is um, given by d theta x, d phi x, d theta y, d phi y, and d theta z, d phi z. Okay, which is given by um, d theta of x, which is cos theta cos phi, is cos theta sin phi, and d theta of z is minus sin theta. And then d phi of x is minus sin theta sin phi. D phi of z, d phi of y is sin theta cos phi. And d phi of z is d phi of z is 0. Right? So now you do this procedure that we did. Uh, so you get this norm of dh as equal to I'm just writing it down. You have to take all 2 cross 2 submatrices and then just uh, yeah, you have to take all 2 cross 2 submatrices and then take their determinants and sum them up. So you get this to be equal to sine theta. Okay. or so when you pull this function back to this theta phi domain, it becomes an integral of f over this theta phi domain, but you have to multiply sine theta with this. And then you can do d theta d phi. This is over this theta phi domain, which is 0 comma pi cross 0 comma 2 pi. Okay, so this is something to keep in mind, that whenever you have the sphere, you can use these what we call polar coordinates. And if you have to complete this surface integral, then just you can pull it back. You can do 0 comma pi, 0 comma 2 pi, and you have the factor that you have to multiply with is this sine theta factor. Okay. Now, the question is, you have the ellipsoid, which we just solved. We know how to solve for this ellipsoid. How do you solve for this ellipsoid? So one way is, of course, using the divergence theorem. So you do divergence of x, divergence of v over this guy. Let's call this ellipsoid as E. So it's divergence of this um, um, over the entire volume of this ellipsoid. So E is a region of space where the boundary of this region is this ellipsoid, and E is the region. So divergence of E over this region. So, well, how do you do it? If you set x and if you set y, z both equal to 0, so then your x will vary as um, your x will vary from, I mean, just for the sake of it, if I write this function as x squared by a squared plus y squared by b squared plus z squared by c squared is equal to 1. If this is your ellipsoid, then your x will vary from minus of 1 minus, sorry, what am I writing? Your x will vary from minus a to a. Your y varies from b times 1 minus x squared by a squared minus to b times 1 minus x squared by a squared. Right? And then your z can vary from minus c times 1 minus x squared by a squared minus y squared by b squared, and c times 1 minus x squared by a squared minus y squared by b squared. And you have this function which is x plus y plus z. Okay, so you can complete this integral. Okay, now this is like a problem that I suggest you try. So this problem would be representing the ellipsoid using polar coordinates, right? So in particular, you could use a set of polar coordinates for this ellipsoid, where you could set this. Wait, what are polar coordinates for? Okay. So you could set this x as, sorry, you could set this z as equal to c cos theta. You could set this y as equal to b sine theta cos phi. and you could set this x as equal to a sine theta sine phi. Okay, so you could use this as a sort of polar coordinates for the ellipsoid, right? And as before, your theta, you can take this theta to be from 0 to pi, and this phi to be from 0 to 2 pi. Okay. Now, what I'll urge you to do is instead of doing this volume integral, you can directly try to solve for this component in with respect to the surface integral. Okay. So I told you how to write the surface integral. So you have this map. So let's call this map as H. You write d of H, which would be the Jacobian matrix. This is your first step. So next step is to compute this norm, where this norm is basically um, the sum of the determinants, squares of the determinants of the 2 cross 2 matrices. This is a determinant actually. Okay, so this is your second step. Now, uh, now the final step is to actually figure out what this integrand is. So V is your vector field, which is given to you as, what is this? This is xy plus yz plus zx. Okay, and you have to do V dot n cap. Okay, now what is n cap? If I ask you, so the n cap is the unit normal. Uh, is basically the unit normal at a particular point, and so the uh, um, right. So yeah, once you take the unit normal, well, how do you take the unit normal? So you have the function which is x squared by a squared plus y squared by b squared plus z squared by c squared is equal to 1. So the unit normal is basically, we have discussed this before. It is given by because the surface is represented as uh, as a level set of this function. If you call this function as psi, so because my surface S is basically psi is equal to 1, so the normal is given by the grad of psi. Okay? So which is x by a squared, y by b squared, and z by c squared times 2. Okay. The unit normal is given by grad of psi times um, times the norm of this. Okay. Um, so this you can compute. Right. Yeah, I mean, this integral is a bit involved, but this grad of phi is equal to 1. So this is x by a squared, y by b squared, z by c squared. Then you can do v dot n. This would be xy, yz, zx times x by a squared, y by b squared, z by c squared. And once you figure out what this quantity is, this is going to be equal to x squared y by a squared plus y squared z by b squared plus z squared x by c squared. But x squared by a squared is equal to, yeah, so now you express this as a function of theta, and then you can just pull back this whole function into the theta phi plane and multiply it with this density. Okay. In particular, I'll ask you to write down what this density function is. We got it to be equal to uh, right. We got this to be equal to sine theta for the sphere. What is this quantity? This is like a homework problem. You can try this problem and let me know next class. Okay. All right. If you have any questions, you can let me know. I mean, I understand that this is like maybe not all of this is something that you have understood. Um, I mean, I could have approached this problem solving class in a different way, where I just pick a bunch of problems where the things look canonical, and then you can just solve them quite easily. But I thought that maybe it's good to give a general technique how to approach these kinds of problems. Um, yeah, let me know if you have any questions. Otherwise, we are at the end of time today.